Morning, happy Monday. Let's talk. I'm going to do a couple problems for you in section 3.1. Or I'm sorry, 3.3. And it has to do with increasing, decreasing again. And then I'll give you some problems to do. And then I'll post a Zoom meeting for tomorrow and we can talk about them. So when you look at increasing or decreasing functions and you think about the derivative, it says derivative is slope of tangent lines. A couple of things can happen. Here's an increasing section of curve that levels out at a point and then continues to increase. Okay, so at this point, the value of the derivative is 0. Every other place along this curve, the value of the derivative is positive because the tangent lines have positive slope. So you say, okay, is this statement true or not? If the function is increasing, then the derivative is positive. And the answer is no, that's not a true mathematical statement because right there, there's an increasing chunk of curve. The y coordinates are still getting bigger even though the function levels off. Remember, this isn't flat through here. It's only flat for that one value of x. Right? So just because the function is increasing doesn't mean the derivative will be positive, because you might have this one situation where you have a flat spot. In general, it is true. But you can flip this over and say it the other way around. If the derivative is positive, our slopes must look like that. So then we do know that the function is increasing. So this is true. Derivative positive, function increasing. You can use the same argument with decreasing. Just because the function is decreasing doesn't mean the derivative is negative, because you can still have a flat spot. But if you say it this way, if derivative negative, then function decreasing, that is true. Okay. If the derivative is equal to 0, you have a horizontal tangent line, not necessarily a max or a min, because you could have a flat spot. So where it's equal, the derivative is equal to 0, those are called critical values. You could have a relative max, a relative min, or neither. Now also remember that when the derivative is undefined, you have critical values also. Right, so these guys are true statements. And we can use them to find increasing sections of curve, decreasing sections of curve, horizontal sections of curve or points of curve, and critical values to find relative max and mins. So the first derivative can be used to find peaks, valleys, flat spots, intervals of decreasing, intervals of increasing. And that's what we're going to do. We're going to make our first derivative table, look at the value of the derivative, and determine what the function looks like. We're always trying to describe the function. So here's some problems from section 3.3. They're on page 186 to start with. All right, so here's my function, x to the 2/3 minus 4. If I graph it, looks like this. Decreases, comes to a corner, and then increases. All right, so we want to find critical values, just like before. That's the first step. Take the derivative, say, okay, if I set this guy equal to 0, I get to here, divide both sides by 2/3. Now I have x to the negative 1/3 equals 0. If I raise this side to the negative 3, negative 1/3 raised to the 1/3, or times 1/3. A power raised to a power, I multiply those together, and I get 1. So I get x equals. Now when you try 0 to the negative third, that's like 1 over 0 to the third, and there's no solution to that. So there is no place where the derivative, where this guy is equal to 0. Look over here, no horizontal tangent lines. Take the derivative and say, well, what makes it undefined? To make a fraction undefined, you need the denominator to be 0, which means x to the 1/3 has to be 0, which is at x equals 0. So this x equals 0 is your only critical value. So to make your first derivative table, you take the x-axis and you divide it into intervals based upon your critical values. So I make a column for 0. The interval to the left of 0 goes from negative infinity up to 0. And at the right, it goes from 0 to infinity. I then check on values of the derivative. Now, you're using the derivative to describe the function. Okay? So if I go and, let's see if I can make this a little lighter. There we go. Go to y equals and type in the derivative. 2 divided by 3 x raised to the negative 1/3. That's the derivative, and look at the table. Second table. Set it up. I'll start at negative 4. I'll count by 0.1s. Second table. All right, negative. So when my values are to the left of 0, the value of the derivative is negative. I can plug a number in. That's what I'm doing here. I'm plugging values of x into the derivative and see what I get. I get negative, and there's the error, derivative undefined, and then to the right of that, that's positive. So derivative, negative, to undefined to positive. When the derivative is negative, the function is decreasing. When the derivative is positive, the function is increasing. So my function is going from decreasing to increasing. It's going down to going up. So that's a relative min. When derivative goes from negative to positive, function has a relative min.